Thank you so much, Dr. Liu, for the very kind introduction. And a huge thanks to the organizing committee for inviting me to give this keynote. I hope that all the attendees in the Buffalo area are staying safe. I have been reading up on the ongoing snowstorm, so please stay safe. I will share my screen, and please let me know if you can hear me clearly and you are able to see my video. Are you able to see my video?
Yes.
Perfect. All right. So as Dr. Liu mentioned, I am Rajesh Parekh. I currently work at Google, and I'm going to talk to you about some of the exciting things we are doing at Google Maps. We really believe that this is a planet-scale playground for computer scientists. So Google Maps aims to build an accurate model of the planet. What you see on the left is an ancient tablet that dates back to the 6th century BC, perhaps the first known map in the world. This has Babylon at its center and a few surrounding areas that were known to the Babylonians at that time. Fast forward about 2,600 years, we now have the map of the entire world on our mobile devices. And that's tremendous innovation. It has really helped us explore the world and get things done in the real world with a lot of ease. While we see Google Maps as a single application, either on our mobile phone or on the desktop, internally, the Google Map is a layered cake of multiple layers of technology that all have to stay in sync with each other. So at the bottom, we have the road network, essentially all of the roads, the intersections, etc. On top of that, we anchor accurately positioned imagery that eventually helps us to create these rich 3D models. And finally, the topmost layer is the semantic information. So when we go to a business and we know that this is a coffee shop, that's the aspect of the semantic information. You can imagine that all of these layers are potentially changing every second. And it becomes incumbent upon us to keep these layers self-consistent so that we can present a holistic experience to our end users. For those of you who have been using Google Maps or any other mapping products, the applications are very well known. In Google Maps, you can find places by name. So for instance, if you happen to be in the San Francisco Bay Area and you want to visit the Coit Tower, you can just type in Coit Tower and it identifies where that place is. If you want to route yourself from where you are to Coit Tower, it helps you get directions and navigates you along the way. In recent times, we have made a lot of advances in providing our users with more sustainable journey options. So you may have seen the eco-friendly routing on Google Maps. Additionally, we are making a lot of effort in providing other options for transit. So beyond just driving, can you use public transit if that is available? Are there walking navigation directions available for short trips, etc.? So all of these are systematically presented to the users so that the users can make informed choices. I just want to share a fun fact with you. According to Google Maps, the longest navigable road trip is from Cape Town in South Africa to Vladivostok in Russia. You can actually drive all the way. Our estimate is that it is going to take about 360 hours of nonstop driving. But this is an example of some of the challenges that we face. Right? We are building a planet-scale application, and keeping this data fresh and accurate as the world around us evolves is one of our most fascinating challenges. More recently, we have also started providing discovery and exploration experiences. So suppose if you happen to be in the San Francisco Bay Area, you want to go to the Mission District and say, well, let me explore, what are the restaurants that are available there, gives you a list of restaurants. You can pick a certain type of cuisine. You pick a particular restaurant and you can actually use some of the street view imagery to pan around and explore that area even before you have gone there. Right? And once you find, oh yeah, this is a great place, I would like to be there, you can go ahead and navigate yourself, find parking, and so on. So this is a full experience that we are able to provide to our users as they go about doing things that interest them in the real world. As you can imagine, mapmaking is very hard. I want to share with you a few challenges that we have faced. Maps are always expected to be comprehensive, fresh, and accurate. But as I mentioned earlier, the world around us is constantly changing. Especially the last few years during the COVID-19 pandemic showed us that there were a lot of changes in local businesses. Right? Some of them closed, others moved, and even those that stayed open had to suddenly change their mode of operation. Right? For instance, restaurants could not allow dine-in or did not allow dine-in, and they offered takeout and delivery services. Similarly, there are traffic incidents, there are road closures due to weather events, etc. And it becomes important for us to try and capture these as quickly as possible and reflect them back to our users so that they can incorporate these decisions in their day-to-day journeys. We use a lot of different techniques to help us curate and maintain the underlying map data. Now, each of these have their own strengths and weaknesses, but essentially a complementary set of data helps us go a long way in our overall goal of presenting a fresh and accurate map. The techniques are web extraction, feeds from local providers, our human operations. These are our human experts who really help us in curating the data and also moderating other data that is available to us. We leverage crowdsourcing, and finally, imagery. Now, in the interest of time, I'm going to focus on the last two data sources, so crowdsourcing and imagery. Let's start with crowdsourcing. We have 1 billion+ monthly active users on Google Maps. And we, as users of Google Maps, can actually provide information back to Google Maps. If we see that something is wrong or something is missing, as users, we can provide this feedback. And then we take this feedback from the users, moderate that content, and feed it back into the maps. There are 50 million or so updates that are made to the map every single day. With Google Maps, you can find information about businesses, their ratings, and so on. We have about 200 million businesses in the world. So you can imagine that there is a lot of information that users are able to share with us. The challenge sometimes is telling the good updates from the bad ones. Most of the users are genuinely interested in providing accurate updates. Sometimes the updates are not good. There may be genuine mistakes that users make, and very occasionally, fraud and vandalism. But these things can have a very significant impact on the quality of the map data. And if this is not caught in time and fixed, it can result in a detrimental user experience. In terms of how we solve for these challenges and curate edits at scale, we originally started with focusing on our human experts, right? And the human experts would evaluate the incoming submissions and decide whether they were appropriate or not. They would try and triangulate them with other sources and so on. As you can immediately see, this doesn't scale. Over time, we have developed a lot of machine learning models and classifiers that help us with the moderation purposes. Now, despite our best efforts, sometimes mistakes do go by. Now, this is an example from a few years ago when Donald Trump won the presidency. An irate user made a change to Trump Tower in New York. Now, in terms of Google Maps, we cannot allow individual emotions or political affiliations, etc., to result in these kinds of vandalism or fraudulent activities. We are constantly working on expedient measures that will help us to fix these solutions. So if there are user reports, we actively monitor media outlets. For instance, Twitter. Here is an example of a business owner who mentioned that their phone number on Google Maps was inaccurate, and actually one of the fraudsters had changed their phone numbers, right? And so monitoring media outlets like this alerts us to potentially erroneous data situations that we can take a look at and fix them. We need to make these fixes quickly and then propagate them across all of the product surfaces rapidly. And those are some of the biggest engineering challenges we face at the back end. You may all be aware of the Street View imagery. Google Street View displays panoramas of stitched images. Essentially, the Street View cars have collected nearly 220 billion high-resolution images over the years from 100 countries and territories around the world. And when you go to Google Maps, you can click on the Street View application, and you can get a very interesting panorama of the area that you intend to visit. Now, for instance, what you are seeing here are the mosaic steps in San Francisco, and you can pan around and identify, okay, this is a popular tourist spot. What does parking look like here? You can see that there is some street parking available, etc. Right? How do we collect this information? A lot of the Street View imagery is collected by the Street View cars. Several of you may have seen these marked cars drive around. But we've also realized that there are several places where these cars cannot necessarily access, either small alleys or places that are inaccessible to vehicles. And we have developed other techniques. So in Southeast Asia, we have these tricycles that have the mounted cameras that can go in the narrow alleys and get Street View information. And then in some cases, we have our trekkers with backpacks that can go and get the imagery from areas where vehicles are not allowed. The map in the center shows you all the places where we have Street View imagery collected. Right? And in some cases, of course, we also have cameras mounted on snowmobiles and on kayaks. Another interesting fact that I want to share with you is that Google Street View cannot be everywhere in the world. And there is actually the ability for crowdsourced Street View imagery. So the folks in Faroe Islands, these are islands in the North Atlantic, learned about our crowdsourcing applications and were very interested in getting the Faroe Islands mapped. And so what they did is they basically mounted the cameras on the back of sheep, and they roamed the sheep around the streets of Faroe Islands. Well, instead of Street View, we got Sheep View, but we were able to map the Faroe Islands all the same. In more seriousness, we really believe that our ability to ask the Oracle important questions like, where am I in the world? Where can I get coffee? Can you show me how to get there? Should be truly global. Now, in order for us to do this, machine learning has been the workhorse in geo for the better part of the last decade. But the advances in deep learning computer vision over the past few years, paired with this rich Street View imagery, has allowed us to extract a large amount of semantic information that we can then provide back on Google Maps. So Street View is a lot more than pixels. Just the single panoramic image shows you that we have the ability to extract street numbers, the street name, the name of the business, If there is the phone number of the business displayed outside. For an intersection, is this a controlled intersection, like it has a traffic light? Are there other traffic signs on the road, etc.? So a lot of this information is extracted by machine learning algorithms applied to these images that have been collected. The confluence of multiple technological innovations, the ability to collect rich imagery, our ability to label data sets. Remember, I told you we work with our human experts as well, and they help a lot with the labeling. The advances in computational power and the deep learning applications have all combined and given us a very unique opportunity to deeply understand the real world around us. Here is an example of how we think about some of the detections from the street view imagery. So essentially, and this is the FRCNN network, and this is published research. We look at this as a three-stage approach. The first is a deep learning model that essentially detects the digits. And this is for the house number, so the street number application. And it detects that this is 9. The second stage is to verify. And you might wonder, well, why do we need to verify this? When the street view car is going around, it is going to just capture all the imagery. And these numbers might be anywhere. They may be on the hoarding by the side of the road. They may actually be the number of a bus that was just going by. So this verification stage looks at imagery at different resolutions and helps us to verify that this was indeed a street number that we are interested in extracting, and not, a bus number, for instance. And then once we have done this, then we transcribe and put it together, and that becomes the street number that is extracted. I just want to give you a couple of examples of the power of street view. So here is a street view imagery from Lagos. And now, if I were to ask you, well, is there a house number here? Even for us as humans, it is going to be difficult. I mean, we may have to look very, very carefully to see if there is a street number there. Passing it through the algorithm that we described, we were able to see that there is the street number right at the bottom. This is the number 22. That's interesting. So now suddenly we are able to detect things that may be hard for human experts to do, and do this at scale. Similar to what Professor Ness Schroff mentioned earlier, context really matters. The real world is noisy. So this is an example of a mailbox. And there are 3 numbers here. There is 15, there is 95, and there is 91 or something. Now, which of these is the correct house number? Well, this is where we take a step back and think about the context, especially in the United States and several other countries. The street numbers are pretty much in order. So if we have the surrounding context, which tells us that, well, I have seen house numbers 905 and 909, then I can be a lot more confident that this house number is 915 and not 15 or 95. And so that's why it becomes important for us to not only take a particular application, but also marry it with the surrounding context that is available to us. I mentioned to you that imagery applications can help us to extract storefront. Right? So this is basically automatic detection of businesses from the street view pano images. As we developed these models, we realized that there were a lot of improvements that could be made to get better performance. So number one, getting representative training data. And all of you who may be in machine learning and AI applications, while these are lessons from mapping, I'm sure that they are generalizable to other domains as well. So representative training data was very important because we realized that originally we were just looking at the street view imagery. These things were collected by cars, and there were several streets that were inaccessible to cars. And so complementing this data with the tracker collected imagery became important, right? And so then that was the comprehensive set of training and test data. Secondly, Over time, we've benefited from bigger and faster processors, right? We use the tensor processing units quite extensively. The newer TPUs enabled us to build training models with much larger images. Now, these street view panels, as you can imagine, these are high definition, very rich images. In order for us to do efficient machine learning, we had to compress these images. But then as the TPUs became much more powerful, we were able to reduce the level of compression, right? And essentially pass larger images through this. And then lastly, improved algorithms. Research is ripe with new algorithms, with better, faster processing algorithms, right, that we are then able to apply to our domain. And collectively, these three approaches were actually able to increase our recall by more than 50%, keeping the precision the same. And that's amazing progress. But it takes systematic experimentation, identifying where the bottlenecks are, and then thinking about how might we address those bottlenecks. Just like we have street view imagery, we also have overhead imagery. And overhead imagery is collected with a variety of different sources. That includes, aircraft, which collects very fine-grained imagery, all the way up to geostationary satellites that, collect coarser imagery for us. This high-resolution imagery, again, is available almost worldwide. It covers about 98% of the world's population today. And what do we use it for? This overhead imagery can actually be helpful in detecting road segments, understanding what is the type of the road. Is this a paved road or an unpaved road? It helps us to model intersections and then connect the road graph together. Here is a very interesting example of a new development, right, that was not originally on Google Maps, right? And so the before photo just shows that this wasn't there previously. And then after applying the algorithm, we were not only able to infer the entire road network, but also connect it to the main highway that is going across that image. Similarly, we are able to draw the buildings. If you see in the Google Maps application, not only do we have the roads, but also the buildings. And getting the outline of the building as faithfully as possible is important because it helps users as they navigate. It becomes like a localization signal for our users. Over the years, we have started building maps for automotive as well. You will wonder, how do we think about this? Well, Google has been building maps for automotive for quite some time. It started with Android Auto. Android Auto has been downloaded more than 8 billion times. This is basically where you can connect your Android phone in the car, and then on the dashboard, you will get a variety of applications, including Google Maps. You could then set your route by saying giving instructions, go to the nearest coffee shop or find Starbucks near me, etc. And then it will help you with the navigation. More recently, we have started working with auto OEMs to identify or to build embedded Google Maps. So these embedded Google Maps are built into the Android system that can run without an Android phone. So essentially, they run on the car itself. The first car that was powered by the Google Automotive Services was the Volvo Polestar 2 that was launched in 2020, and more manufacturers and more models are coming soon. Over the next few slides, I'm going to highlight some of the data modeling work that helps to build the maps for these automobiles. Firstly, we want to empower advanced driving features. So now, as we get into the automotive applications, we are thinking a lot more about attributes like speed limits. What are the signs, right? The school crossing signs, the safety signs. Provide alerts for intersections. Are these controlled intersections like there is a traffic light or a stop sign? Additionally, as more and more automobile manufacturers move towards either hybrid or electric vehicles, energy efficiency becomes crucial. And we have to think about what is the slope, how many stops are there along the path, so that the route can be effectively planned, keeping the battery life in mind. Now, you may ask, with all of these sensors that are available and installed in the vehicles, why do we still need this rich data from maps? The thing is, a lot of the information is actually needed before we start the trip. So for instance, the energy information is needed so that the route can be appropriately planned, depending on the elevation, the stop signs, etc. And in other cases, the maps data helps as a secondary system that complements the onboard sensors for safety applications. Sensors can reach very high amount of accuracy, but when paired with maps, it gives you a much better chance at keeping the vehicle safe. With these data types the map products requires, we have to think about data quality and product quality of the overall map. As I mentioned before, we have our users who can improve maps. They can improve the quality of the map by providing user submissions, Q&A, etc. And they also help with machine learning training. And here is an example of reCAPTCHA, where this is an intersection and it's asking you to label some stop signs. And in some cases, we also have an app called the Google Opinion Awards, where you can occasionally be asked a question, right? And there is a simple answer that the users can give. Collecting this information then helps us to build the ML training models, right? And for the community that is out here today, a few of the things that we think about are how might we enable user submissions in a much more lower friction way. So what are the computations that may actually be done on the edge device and then provided to Google, right? So if the user is taking a photo, can we actually extract some of the information and confirm it with the user first before they are submitting it? Right? Those are the types of open questions that we are thinking about. The drivers can also improve maps. Drivers with active navigation sessions in Google Maps can opt in to have their navigation logs donated. Now, these logs have become one of the most valuable sources of data that have helped us in the auto use cases. Here are two examples of how we have benefited from this information. So DeepMind and Google Maps collaborated in building a graph neural networks model that improved the prediction performance and reduced failure cases. So this is the ETA prediction. When you plan a route in going from point A to point B, we tell you that it's going to take you approximately 26 minutes. We want to be as accurate as possible. Again, leveraging a lot of the information that was provided by the navigation logs helped us to reduce the failure cases and improve the accuracy. And then the other one was just looking at the speed patterns, right? And helping us identify where might be the traffic lights, right? So red light is for stop, green light is the flat line, the V is the red light essentially, and the flat line is the green light. So beyond these applications, again, logs could be used for other applications like detecting speed limit changes, right? Turn restrictions, etc. And we can confirm the existence of this information and feed it back into maps. We have a lot of challenges, of course, and I'll highlight a few of them. Firstly, as I mentioned, we're thinking about Google Maps as a global product. And there are a lot of regional differences all over the world. Fewer than 5% of the intersections are controlled by stop signs in UK and Netherlands, and by yield in Canada. There is only one stop sign in all of Paris. Yield signs no longer exist in Japan, so they've systematically taken them out. And driver patterns or driving habits can also change, right? So for instance, in Japan, stop signs are shaped like yield in other countries. Right? As I mentioned, the driving habits might be different, where drivers in Europe treat stop and yield sometimes very similarly. And two-wheelers in some countries might take some more liberties in skirting direction restrictions. There is real-world churn. So here are a few examples from Street View. Right? You will see that there was metering previously as the cars entered the freeway. Over a period of time, a later image showed that the metering was removed. Speed limits might change, 25 miles per hour to 30 miles per hour. There is a lot of new construction that's going on in the world, right? An entirely new development comes out. So now these are new buildings, new roads that are constructed that need to be reflected in Google Maps. Local businesses might have their information changed, right? And very often these businesses are only providing the changed information on their storefront in handwritten ways like this, like it says open now from 12 noon to 9 p.m. So we have a lot of challenges even with crowdsourcing. People can only help when they see the issue. People can hardly help while driving, so we have to think about low friction ways, right? I mean, if you're driving, we don't want anybody to be interacting with the Google Maps application, right? It should just be, let's say, Google Maps voice directions giving you that, but it's hard for the user to provide feedback. And people can only verify when they know the ground truth. And the ground truth around us might be harder to verify, especially for smaller businesses, for smaller roads, and so on. And as always, there are a lot of edge cases. Despite the best intent of the machine learning models, right, we will have several edge cases. So here on the left is an example of a road where the painted speed limit is 60. What we are seeing on the signs is 40. There is another 50, etc. So now, which of these ones is the correct speed limit? Right? There is a lot of occlusion and other challenges. Right? The signs are old. They have been there for many years. There is either some shrubs that have grown over, or in the snowstorm, the sign is covered. And so how can we effectively handle this? And if we have the assumption that this information is close to real world, it's going to be hard for the machine learning algorithms themselves to completely solve this problem. And this is where the AI plus human intelligence comes into play. We also leverage simulations and other techniques behind the scenes to help us handle some of these edge cases a lot more effectively. I've given you a whirlwind tour of some of the interesting problems and challenges that we face. Looking ahead, a few interesting things. Augmented reality is becoming very, very popular. And essentially what we want to do is to annotate the world around us with useful information at key moments. So suppose if you are walking, this is walking navigation, you hold your phone, it is leveraging the information that's already available in terms of landmarks and other things that we have collected for Google Maps. It localizes the phone and then tells you, where you might want to cross the road or walk across, etc. More recently at the Google I/O, we launched over 250 photorealistic aerial views of global landmarks, right? These are great ways for user to explore places that they may want to visit or they may want to spend time. So here are examples of the Tokyo Tower, the Acropolis, and others. And this is building towards a very rich, immersive experience. And this experience is actually created by effectively fusing both our overhead imagery that was collected from satellites as well as the Street View imagery. Additionally, users are constantly craving for richer maps. Over the last few years, we have started modeling sidewalks, crosswalks, providing real road widths, controlled intersections like traffic lights, stop signs, etc., information about pedestrian islands. So what you are getting is a much richer map that you can then leverage both while driving as well as while walking. So, on the left, you see the old version of the map where the streets were essentially of the same width. Now we have the actual road widths, the crosswalks are labeled, and so on. And that's the essential piece of the next generation mapping applications that we are developing. I hope that these opportunities were exciting for you. You can be part of this journey for the students who are there. There is careers.google.com/students. Please feel free to take a look. There are some internship opportunities, some full-time opportunities, and new opportunities get posted all the times. For faculty members, the research arm of Google is very well engaged with the faculty members as well. And research.google.com/outreach is, the site for you. I think I will end at this point and see if there are any questions.
My name is.
Yeah, thank you.
So before I take any questions, I just want to say a huge special thanks to all of my wonderful and talented colleagues who make working at Google so much fun. While I have presented here, this is the work done by a lot of talented team members. So huge thanks to them.
Thank you so much, Rajesh.